All right, ladies and gentlemen, welcome to chapter 36, which is about magnetism. This is the last set of chapters that we are going to do this year, chapters 36 and 37. But anyway, magnetism is created anytime there is an electric charge. So, a moving electric charge, an electron moving around, is going to produce some kind of magnetic field around it. And so, if you break it down into its most basic principles, basically atoms like iron, nickel, and chromium that have magnetism associated with them, typically there's something going on with their electrons moving around inside of their atoms. So electricity and magnetism were long thought to be completely unrelated ideas, unrelated phenomena. Then just by accident, a couple of scientists, I can't remember who they were, brought a magnet close to a current carrying wire. And what they saw was a deflection. Actually, it was they brought a compass near a current carrying wire, and the magnet started to kind of go crazy. Well, who finally explained it was a guy named Michael Faraday, who was not a great mathematician in terms of what he was able to do with science, especially, he is one of the, big formers of electric motors and things like that, and, got those in the works. But he was able to kind of visualize things very well. And so it wasn't so much his math, but seeing what he saw and being able to explain it on a piece of paper for people, drawing him pictures, he was quite good at. So ultimately what Michael Faraday does is takes magnets, places them in the presence of current carrying wires, and he brings up electric motors. He starts the most fundamental electric motor, and then that is improved upon over the next couple of centuries, or next century and a half or so. And now it's something we can't deal with in our lives without it. And so it led to radio, led to television, lots of different things came along as other people saw what was happening with magnets and electricity. So one of the most fundamental things about a magnet is that it has poles. And there's a north pole and a south pole on any magnet. And so these poles, if they are alike, are going to repel each other. If I try and bring a north together with a north, a south together with a south, it's going to push away. If I bring opposite poles together, they will attract. And if you've ever played with a magnet, you try and push the magnets together. Sometimes they push away. And if you bring them together, watch out. If your fingers get stuck in between, you can give yourself a little bit of pinch as they attract each other and click and stick together. So magnets do exert forces on each other. They're similar to electric charges in that they can both attract and repel without touching. But with these electric charges, the strength of the interaction, again, depends on the distance of their separation. We are not going to look at a mathematical law on magnetism, but it is a distance square law as well. So electric charges produce electrical forces, and regions around magnetic poles produce what we call magnetic forces, give us a magnetic force field. And so in this picture here, we've got a big electromagnet right here on this junk scrapyard device that's used to pick up lots and lots of recyclable materials like iron, throw it into this dumpster, and then they go melt it down and so on. But in this case, which is more powerful, the magnetic field or the gravitational field? And because we are able to lift the iron up off of the earth and away from the earth, the magnetic field is stronger. Again, gravitational field is quite weak. So if we take a bar magnet, hold it by its center, by a piece of string, something like that, it will act just like a compass. Essentially, there's an end that is going to point northward, which we call the north-seeking pole. And there's an end that points southward that we call the south-seeking pole. More simply, we just simply call these the north and the south poles. But all magnets will always have a north and a south pole. If you break a magnet into smaller and smaller pieces, each of the smaller pieces has a north pole and a south pole. Now, why this is set up is something that's a little bit strange, but has to deal with how the Earth is set up. The Earth is set up as a gigantic magnet itself. But where do we find the north pole of the Earth? It's actually at the South Pole. And so that's why the south end of a magnet is attracted to the South Pole. It's because there is a north magnet down there from the Earth, and vice versa for the Earth at the North Pole. It's actually the South Pole of the Earth's magnet that is up at the North Pole. So it's a little bit backwards. It's probably misnamed if you want to think of it that way. But kind of an interesting, just sidelight there. If we had some more time, I would talk to you about it more in depth, but we're kind of running out of time, so we're going to just sort of skim by it there. So if we look at magnets, we've got a horseshoe magnet, we've got a round magnet, we got a little bar magnet there. Each one of these has a north and a south end. And so here in this one, I don't know if you can quite see it, but this is the North Pole, the South Pole, this is the North Pole, this is the South Pole. Can't really tell what the magnet here that is circular is without a little bit more information. But if I were to bring this north over to here, it would stick. If I were to bring this south over to here, it would stick. But if I flip this magnet around, it would want to repel off of the horseshoe magnet. Now, magnetic poles behave similarly to electric charges in some ways, but there are definitely some differences. Electric charges can be isolated. We can pull an electron or proton away. We can't do that with a magnet. A magnet always has to have one end of it be north and one end of it be south. And so break a bar magnet in half. Again, each half is going to have the aspects of a complete magnet. It's going to have a north side. It's going to have a south side. Break it in half again. Now you have 4 complete magnets and so on and so forth. But each magnet would be having 2 complete north and south poles. So here is one magnet broke into a bunch of different pieces. We always have a north side and a south side, no matter how small the pieces get. And so if we were to carry this down to the atomic level, basically what we would see is anything that is magnetic or has magnetic properties, the atoms themselves have a north and a south end to them. So does every magnet necessarily have a north and a south pole? Your answer should be unequivocally yes. And so how do magnetic poles affect each other? Again, like poles will repel and opposite poles will attract. Now, Just like electric particles generate an electric field, so do magnets. Magnets, anywhere around a magnet, you will see a magnetic field generated around that magnet, and it will always flow in a specific way. It will always flow from the north to the South Pole. And so this is a little experiment that you may have seen somewhere along your educational days. It's typically done in elementary or middle school, where you can take a magnet, you can throw it onto a piece of paper, and you can sprinkle iron filings around the magnet. And what we see is this definite pattern. It's almost circular here in the middle, and then it actually has a much larger amount to it there that becomes circular and comes back around up here. It's very concentrated at the ends because this magnetic field is always stronger by the poles. Now, the shape of this field can be revealed by magnetic field lines, just like we saw with gravitational field lines or electrical field lines. Again, we would describe them through the closeness or the length of the arrows that would give us the stronger. Again, we would want them to be vectors. We would want to put arrows on them, again, flowing from the north toward the south. And so magnetic field lines, again, spread out from one pole, curve around the magnet, and return to the other pole. Now, some kind of interesting things happen when we put some magnets together. Here, we can see these two magnets actually beginning to attract each other. If we look at the magnetic field lines here, the north is attracted to the south. The north here is attracted to the south. So opposite poles, again, near each other are going to want to attract, and these are actually sort of pulling toward each other. If we look at this one, we can see a definite line of these iron filings that is set up there that shows the repulsion that is blocking those two from coming together and actually pushing them apart. And so if we also look at a bunch of compasses that are arranged around a magnet, one thing that we can see is that they will arrange themselves in a pattern that is akin to the general shape of the lines that would leave the north and head towards the South Pole. And so you can see all of these compasses are aligning to those magnetic field lines. So what is the direction of the magnetic field outside of a magnet? It always heads, again, from the north toward the south. Here we're going to skip 36.3 and 36.4. Again, they're interesting, but just a little too specific, getting us away from just the general basics that we're trying to cover here before the end of the year. But 36.5 has to deal with electric currents and magnetic fields. When we have a wire that has an electric current passing through it, what we see is around that electric current, a magnetic field is generated. And again, this begins to show kind of that interrelationship between magnets and electricity that, they were once thought to be completely separate things, but definitely have some things that go on that are the same. And so a moving charge will produce a magnetic field. An electric current that passes through a conductor, a wire, something like that, produces a magnetic field because, again, we have those mini charges, those electrons flowing through the wire, And as we have that motion of the electrons, we generate a magnetic field. Now, the magnetic field that surrounds a current-carrying wire can be shown by arranging magnetic compasses around the wire, much like we just did with the electric compasses around the magnet. If we put the compasses around the wire, we will see that they change their direction in different positions around the wire. So these compasses are going to line up in these different concentric circles. And when the current then reverses direction, basically what happens is that the compasses turn around. And this just shows that the direction of the magnetic field is also changing when the direction is going somewhere else. And so here we have that wire that has no current passing through it. And here we have the wire that does have electricity passing through it. We can see that the directions of the compasses change everywhere. Here, they're just aligned with the Earth's magnetic field. Now, if I have a current carrying wire, we have the arrangement of these sort of little loops that show the magnetic field lines. If we create a loop in that wire, what will happen is that loop will actually create more of a magnetic field in the same place. So by creating mini loops, we actually can generate a very strong magnet by creating many more loops. And so when we take a current carrying wire and coil it into many loops, we generate what is known as an electromagnet. And so iron filings that get sprinkled around one magnet. I'm not sure if you can really see this. We just see the nice circular pattern. If you look at this one here, basically what you will see, this picture is in your book, by the way, you will see that the magnetic field lines get more close together when we do a loop. If we do several loops, those magnetic field lines get very tight in there as we generate much more of a magnetic field. But sometimes a piece of iron can be placed inside the coil of an electromagnet. This will increase its ability to be a magnet. But at a certain point, the iron sort of saturates with the maximum amount of magnetic field that it can hold. And so if we're going to make an electromagnet, generally the strongest electromagnets are not going to be made out of iron. We're going to make them out of something else. But we do have these superconducting electromagnets. It can generate very powerful magnetic fields for very long periods of time without using much power. And we do have to use some power. It says without any power. You do have to indeed do a little bit of power there. But at Fermilab near Chicago, there are these superconducting electromagnets that do guide these high energy particles, these electrons and protons, around this big 4-mile circumference accelerator. And basically they slam these particles into other particles and get them to break apart. We also see superconducting magnets in MRI machines, these magnetic resonance imaging machines that are used in hospitals. If you have, a problem with your knee or something like that, you may have to have one of these MRIs. So last slide for this set of notes. Why does a current carrying wire deflect a magnetic compass? Well, it is because the magnetic compass is being entered into a magnetic field generated by that current carrying wire. So that's it for part 1 of 36 notes. We'll get to part 2 here very shortly, and I promise I will turn off my email.